Okay, this is our second video lesson. I should be able to get the next few examples done in just this video, and then that'll be it. Okay, example 6. And I know I've skipped a couple of problems. This isn't our sixth example total. That's okay. So two small airplanes start from a common point A. That's not on the picture, so let's draw that. There we go. At the same time, one flies east at a rate of 300 kilometers an hour. The other flies south at a rate of 400 kilometers an hour. After 2 hours, how fast is the distance between them changing? So, variable, or sorry, equation relating all the stuff I have. We'll just have, since we have a horizontal distance and a vertical distance, we'll just call those x and y. So it's Pythagorean theorem, right triangle, x squared plus y squared equals d squared. I have dx dt, that's 300 kilometers an hour. I have dy dt, it's 400 kilometers an hour. And I want to find dd dt, the derivative of the distance with respect to time, specifically at time equals 2 hours. So I always start after that, after I set up my variables and my rates, make sure I have everything, derivative of x, derivative of y, derivative of d, all my variables are covered with this equation. And I know 2 of them. If I only knew 1 of them, this could be a problem. Take the derivative of both sides of my equation. Got some chain rule. 2x times dx dt plus 2y times dy dt equals 2d times dd dt. And I could divide everything by 2 if I wanted to. I didn't do that for this problem, but you could definitely divide everything by 2. Now specifically in this problem, they said when time equals 2. So when time equals 2, my x is equal to 600 kilometers because it's going 300 kilometers an hour. So after the first hour, x equals 300. After the second hour, x equals 600. After 2 hours, y is equal to 800. After 2 hours, d is equal to 1,000. And you get the 1,000 from using Pythagorean theorem. So 3, 4, 5 triangle, this would be 600, 800, 1,000. So I can plug in those numbers, x, y, d. I can also plug in dx dt and dy dt. So 2 times x would be 1,200 times the given rate for x, plus 2 times y is 1,600 plus the given rate for y equals 2 times 1,000 dd dt. You solve that and you get 500 kilometers an hour, which actually kind of goes to show that you could do this problem without related rates, because if my original triangle is 300 by 400, my distance is changing by 500 kilometers an hour, because I'm starting at like a 3, 4, 5 triangle the first hour, then times 2 I'm going to a 6, 8, 10 triangle for the second hour, or times 3 would have been 9, 12, 15 for a 3, 4, 5 triangle with a multiple of 3. So it's changing by 500 kilometers an hour. All right, number 7. Number 7 is a ladder problem. So a 13-foot ladder leans against a vertical wall. The bottom of the ladder is slipping away from the base of the wall at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when the ladder is 5 feet from the base? To be careful with ladders. A lot of them have like little stickers on them that say you need to have it at this level, because if you lean it against a wall and you're too steep, it can fall backwards. If it's too wide, it could slide down. When I was in high school, I worked with our youth group. One of the things that I did was I helped set up lighting on our stage. And so we'd put ladders up, or we'd go up on the trusses or whatever, and we'd change the lighting out for what we were doing in the gym, or whatever. And a friend of mine went up on a ladder, and nobody was holding the ladder, and it wasn't at the right angle, and it totally slid out. He must have fallen 20 feet. He didn't break anything. I have no idea how. Because he literally probably fell 20 feet. It was high. I mean, it could have been 15 feet, but seemed really, really high. It was definitely more than 10. Anyway, got to be careful about sliding ladders. There's a takeaway for today. All right, I want to use x and y for my horizontal and vertical. So x squared plus y squared equals 13 is my equation relating the three sides of the triangle. The difference between this problem and the last problem is that, just like with the cone and the cylinder, you had a number that was a variable in one problem, the radius, and in the second problem, it was a constant. In the problem that we just did, the vertical, the horizontal, and the diagonal were all variables. In this one, though, the 13 is a constant. So dx dt is given to me, 2 feet per second. dy dt is not given to me. That's what I'm trying to find. And dy dt should be negative. I would say that dx dt is positive because you are taking the distance between the base of the wall and the ladder, and you're making it greater. But for dy dt, that's going to be negative when we find our answer because you're taking the distance from the top of the ladder to the ground, and you're making that smaller. And again, the 13 is a constant. So I take the derivative of both sides with respect to time. On the left-hand side, I get 2x dx dt plus 2y dy dt. And on the right-hand side, I get 0. Plug in my x and my y. They said when x equals 5. So when x equals 5, this is a 5, 12, 13 triangle. Nice Pythagorean triple. Plug in my numbers and solve. All right, this one's called example 10. Just checking. I guess that's my last one. I skipped a few just because they were very similar to other problems. Okay, so last problem. This one's going to use a little bit of trig. A television camera at ground level is filming liftoff of a space shuttle. It's rising vertically according to the position equation 50t, s equals 50t squared, where s is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. Find the rate of change and the angle of elevation of the camera at 10 seconds after liftoff. So as the ship goes up, the camera is going to go from looking straight horizontal to looking up higher and higher. So I need an equation, if I look at the diagram, relating s to 2,000 and theta. So we'll call that tangent. Tangent theta equals s over 2,000. The other things that I know s is equal to 50t squared. So s, in this second equation, s equals 50t squared, s is an explicit function. But in the original equation, we just wrote tangent theta equals s over 2,000. S is an implicit function. We want to find, let's see, we know, what rates do we know? Find the rate of change of the angle. So we need d theta dt. We're going to find that when 10 seconds have passed. So if I take my original equation that I wrote down, tangent theta equals s over 2,000, and you could plug in the 50t squared. I didn't do that, but you could just plug in the 50t squared and work it out from there. So I took the derivative of both sides, derivative of tangent with respect to time, tangent theta, and then derivative of s over 2,000. Derivative of tangent is secant squared, and then times d theta dt. Derivative of s over 2,000 is 1 over 2,000 times ds dt. So again, I could have just plugged in the 50t squared and gone from there. If s is 50t squared, ds dt is 100t. When t is equal to 10, I go back up to this diagram, t equals 10, I plug that into 50t squared. So 50 times 100 is 5,000 for s. So tangent theta is equal to 5,000 over 2,000, or 5 over 2. So you can use your calculator to get theta. It's the inverse tangent of 5/2. You can plug all that stuff in. I need the secant squared then of that angle theta, which is the inverse tangent 5/2. I have my 1/2000 times 100 times 10. So work out that math carefully, and you get 0.069 radians per second. So that's the angle of elevation from the camera. It's going up 0.069 radians per second. So for most of the homework, it's out of the book. Some of the problems you'll get really easily. Some of them you get stuck. As usual, you can use the answer keys to try to give you tips on how to go. And then usually we spend quite a bit of time in class going over some questions. I posted lots of different answer keys, so just look at everything and then feel free to jump on and ask questions. Thanks, guys. Hope you have a really good week. Hope things are going well for you. All right, talk to you later.